Hi, I'm Guang, 15 years old. In this lesson of the techniques and applications of definite integration, we are taking a look at this example we had from a previous lesson. So, this question over here, where we have to determine the volume of the region formed when you have an intersection of two cylinders. The first cylinder is x squared plus y squared is equal to 4, and the second cylinder is x squared plus z squared is equal to 4. So if you have watched that lesson, then you will probably already know that these two cylinders, they are similar in shape, but they are just in different directions. X squared plus y squared is equal to 4 extends in the z-axis direction, or for x squared plus z squared is equal to 4, that extends in your y direction, right? So with that, the two methods we used in the last lesson are both Cartesian coordinates. Well, one we first integrate with respect to y, the other we first integrate with respect to x. And we do find that integrating with respect to y first is actually much simpler. But other than using that, do we have any other different methods? So since this is a double integration, you can change it into a triple integration, of course, or you can also take it as a double integration. It depends on how you like to solve it. So in this lesson, we are taking a look at the third method. So in this third method, we'll find the volume. Once again, we can split this into 8 separate octants. Since this shape here, it actually has the same amount of volume in all 8 octants. So you can just take the first octant and multiply that volume by 8. Alright, so 8. And what are we going to have inside here? So in the last time, what we changed, or what we had was z is equal to square root 4 minus x squared. So we changed the second cylindrical, well, I guess you could say cylindrical function into z is equal to square root 4 minus x squared, right? And that was our integrand. Since if you want to integrate from in the z direction, that would just be from 0 to this, which is basically directly your integrand. But in this case, how about we change your coordinate system? And in this case, we take a look at polar coordinates. Now in polar coordinates, square root 4 minus x squared, x is r cosine theta. So when you square that, this is what you are going to see. So which means this is actually going to be our new integrand, since you do have this amount of height on a certain area that you have. So you're going to have square root 4 minus r square cosine square theta. And of course, last time we had dx, dy. So in this case, we're going to have r dr d theta. Okay, so this is what we have. Now let's integrate with respect to r first. Well, when we integrate with respect to r first, your radius is from 0 to 2, while your theta is going to be from 0 to half pi, because you have to be aware, once again, this is just in your first octant. Alright, so this is the kind of integration that we are dealing with. Now, you can put this r within the dr, so you have a negative 4 on the outside. Then you have to integrate from 0 to half pi, then integrate from 0 to 2, then you have square root 4 minus r square cosine square theta. Alright, so when we put the r inside and an extra negative, we are going to have d negative r square, right? But how about we try to change it so that it is kind of the same as whatever is in your integrand. So how are we going to change that? So of course we are going to need cosine square theta here, which means you have to divide by a cosine square theta in front. And before here, you can just have a 4. So afterwards, you just have to d theta. Right, so this is now the kind of integration we have. And we will just have to integrate this. Well, since this is to the power of half, which means you have to multiply by 2 over 3, which is now 8 over 3. Then integrate from 0 to half pi, and you are going to have. So since you integrated that, and 1 over cosine square theta will stay the same. Now, square root 4 minus r square cosine square theta, then cube, and you can substitute in the values of 0 and 2, and at last d theta. Right, so this is what we are going to see. Now of course, when you substitute in 2, you will be having, well, 4 minus 4 cosine square theta, where you could take out the 4's. So, which means we would actually have to separate this into 2 separate parts. And by 2 separate parts, they are going to look like. So, in your first term, you're going to have 8 sine cube theta. Since we have substitute in the 2, you could take out the 4's, they go through a square root and a cube. Or for the rest, you have a 1 minus cosine square theta, which becomes a sine square theta, which goes through a square root and a cube. Right, and at last, you're just going to have to put in 0, which 0, that means this part behind is 0, and you just have square root 4 cube, which means you have minus 8. And now, this is what you're going to have to solve. So, we can proceed with whatever we had. Well, we could take out both of these 8's. So you have negative 64 over 3, integrate from 0 to half pi. And what are you going to have? So you have sine cube theta over cosine square theta, then d theta. Or for the other part, that is plus 64 over 3, integrate from 0 to half pi d theta over cosine square theta. Okay, so in your first term, you're going to put a sign into the d theta. Then you are going to use your identity on the numerator, which you will see 64 over 3, integrate from 0 to half pi. So with that, when you put it inside and you use the identity, you're going to have 1 minus cosine square theta on the numerator. And you're going to have d cosine theta. Right, so that will be what the first term becomes. So now you look at the second term, where you have a secant square d theta. So if you're familiar with these integration formulae, you will know this is 64 over 3 tangent theta. Then substitute the values of 0 and half pi. Okay, so that is what we see. But then you might realize, tangent half pi, isn't that just infinity? So why don't we just substitute in infinity and get a final answer as infinity? But let's put it there first, alright? So we will just leave that as a limit form, okay? Well, for the other part, which is tangent 0, well, that's just a 0. So let's take a look at what we have in the first term. We're going to have partial fractions, or you could just say separating them, simplifying them, whatever. So 0 to half pi. What you actually have here, since you separate them, you have 1 over cosine square theta. You can have, so when you integrate this part with respect to cosine theta, of course you could write out once again the integration, or you could just directly choose to integrate it. You're going to have a negative 64 over 3 1 over cosine theta. Then here you're going to have to substitute in the values of 0 and half pi. Alright, so this is what you have from your first term. Now in the second term, you're going to have minus 1, which is just minus 64 over 3 cosine theta, substitute in from 0 to half pi. And then you have to add 64 over 3 limit theta approaches to half pi tangent theta. Alright? So this is what we will see. Right, now once again, let's take a look at the first term. Now the first term, when you substitute in half pi, you'll realize that is over 0, which is an infinity, which then you'll realize you have a positive infinity and a negative infinity, which is going to give you an indeterminable form, which we will have to solve later. And then if you substitute in 0, this part will just be 1, where you have to add on 64 over 3. So 64 over 3. Now we take a look at the second term. You put in half pi, you're going to have 0. You put in 0, you're going to have a negative, and then you add on 64 over 3. And for the remaining parts, you just have 64 over 3 limit theta approaches to half pi tangent theta minus secant theta. Well, since secant is basically 1 over cosine. But of course, well, does that look solvable? Doesn't really seem solvable, isn't it? How about we change them back into their sine and cosine forms? Then you just use common denominators on them in order to get something over cosine theta, since both of them have over cosine theta, while the numerator is going to be sine theta minus 1. Alright, so at this point you have a 0 over 0 form, which is also indeterminable, but using special limit methods, what you can have is, well, a simpler method would of course be your L'Hopital's rule. So L'Hopital's rule, sine becomes cosine, and then you're just going to have a negative from this cosine, and that becomes over sine theta. Right, now you can substitute in the value of half pi. So when you substitute in the value of half pi, you're going to have a 0 over 1, which is just 0. And thus, you get the answer of 128 over 3. So this answer is consistent with the previous methods. So this is pretty much the entirety of method 3, where we used polar coordinates to integrate with respect to r first. Alright, so just take a quick look at all of this. Alright, so essentially you just used the function of one of these cylinders, then you use whatever polar coordinates you have, and with these polar coordinates, well, you just put in the r to the back, integrate them, substitute in, and then using a few trigonometric tricks, identity, and of course a basic formula, and then afterwards you just have a L'Hopital's rule. Alright, so I hope for this lesson you're clear of all of these so far. I'll be ending this here, and thank you for your watching.